So, yes, so let's resume. So it's for me a pleasure to introduce you Francois Golse from École Polytechnique. He's going to give us a talk about empirical measures and quantum dynamics. Francois, the floor is yours.
Thank you very much for the introduction. Thanks to the organizers for putting up this very interesting conference. I'm very sorry for not being able to attend in person and meet all of you guys. It would be a pleasure. So I want to report on some joint work with Thierry Paul, which appeared a couple of years ago in Communication Maths Physics. So maybe as a motivation, let me recall a few facts and notation about the mean field limit in quantum mechanics. And here I'm referring to an old paper by Herbert Spohn, which appeared in 1918 in Reviews in Modern Physics, beautiful paper, which contains a lot more than mean field limits and quantum mechanics. So here I'm going to consider the n-body Schrödinger equation, where the unknown is going to be an n-body wave function, psi n, complex valued function of time, and the positions of the n variables, x1, x2, xn. And this wave function evolves according to the Schrödinger equation here, where the quantum Hamiltonian is this operators, this differential operator here, involving the kinetic energy of the n particle system and the potential energy with a coupling strength of order 1/n. So here it's a scaling which is typical of the mean field limit for bosons. So here you have pairwise interactions between particle at the position j and k for all j and k between 1 and n. So that's the n-body dynamics. On the other hand, you have the mean field dynamics, which will be the Hartree equation. So here the unknown is going to be a wave function, but a single body wave function. So here you have just one position variable. It's a complex valued function. So obviously you want to approximate in the limit as n tends to infinity, psi n somehow by this psi, which obeys a similar Schrödinger equation here, except that it's in the one body space. So you just have the kinetic energy of the typical particle. And here you have the mean field potential, self-consistent potential, which is obtained by taking the convolution x of the potential with the square modulus of the wave function. And the mean field limit tells you that if you look at the reduced density matrix, which you built out of the n-body wave function. So in other words, you take psi n bar, and you integrate over all the position variables but one, and you make the positions of, say, the second to the n particle coincide, and you integrate over the z2, zn. So this should convert as n tends to infinity to psi of tx, psi bar of ty, where psi is the solution of the Hartree equation. So the problem here would be to find a convergence rate, and possibly a convergence rate that's going to be uniform in h bar, uniform independent of h bar as much as possible. That's quite desirable if you remember that h bar is a rather small parameter. If you compare it to the typical action of some particle in some regimes, it can be small, right? So it's desirable to have a convergence rate that is as much as possible independent of h bar. Okay, so of course we know that when the typical action of the particles is large compared to h bar, to the Planck constant, the quantum mechanics is approximated by classical mechanics. So it's a good idea to give a look at the classical situation. And here it's going to be the part of the talk which is mostly devoted to kinetic equations. The rest of the talk will be more about quantum equations, but as an excuse, I want to say that much of what I'm going to say is going to be inspired by the kinetic model, as a matter of fact. Okay. So here a diagram to summarize the situation. So the limit which I was describing before is this horizontal arrow here, going from Schrödinger to Hartree, and the corresponding limit in classical dynamics is you start from the n-body Liouville equation, and as n tends to infinity, you hope to derive the Vlasov equation. Okay, and of course, as h bar tends to 0, which is sort of mathematical formulation of the fact that you're looking at the classical regime, classical limit, you expect that the Schrödinger should converge to Liouville, and that the solution of Hartree should somehow converge to the solution of Vlasov via some classical limit involving, for instance, Wigner measure, if you want. I will return to that later. So at the moment, the mean field limit in classical mechanics involves Newton's second law written for each particle. So Qj is going to be the position of the jth particle, Pj its momentum. So Newton's second law tells you that Pj dot is equal to -1/n, the sum of the gradient of the potential at Qj at time t minus Qk at time t, and you sum for all k different from j between 1 and n. And here again, you find the coupling constant 1/n, which is typical of the mean field scaling here. All right, so the classical analog of the Hartree equation, as we know, is the Vlasov equation, which is written here. The unknown is the distribution function f of t, x, and psi, non-negative. And it's del t of f plus the Poisson bracket of the mean field Hamiltonian, which is written here, 1/2m psi square in norm, plus the self-consistent potential Vf of t and x, which here again is obtained by taking the convolution of V in the x variable with the macroscopic density, which is about the same as taking the convolution product of V in x and psi with F, right? So that's the mean field potential, the self-consistent potential, and you move F by the Poisson equation corresponding to this Hamiltonian. Now, going from Newton to Vlasov here means that you're going to look at the n-particle empirical measure, which was already mentioned this morning by Thierry. That's very much the same approach. So you look at 1/n, the sum over j of the Dirac measure at Qj, Pj at time t equals 0. And if you assume that this converges weakly to the initial condition for Vlasov, then you would like to see that in the limit as n tends to infinity for later times, the empirical measure built on the Qj, Pj at time t converges weakly in the sense of probability measure to f of t, which is a solution to the Vlasov equation. Now, that's one formulation of the mean field limit in classical mechanics. And specifically in classical mechanics, this approach is based on the following observation, which apparently goes back to Klimantovich not so long ago, in the early 60s, I believe. So the observation is this. So here I claim it's a theorem, but I think that Klimantovich would probably not write theorem because I think it was more a physicist, a theoretical physicist. So the idea is that if you assume that V is C1 with Lipschitz continuous gradient, and if it's even, then to say that the n-tuple of position and momenta, Q1, P1, etc., Qn, Pn of T, satisfies the system of Newton's second law. This is equivalent to saying that if you look at the empirical measure built on this n-tuple of positions and momenta, this is a weak solution of Vlasov. And the proof is rather easy. Because the fact is that since V is C1 and even, the gradient of V at the origin is equal to 0. And if you look at the interaction term that appears in Newton's second law, 1 over n, the sum over k, for k different from j, of V qj minus qk, first, because grad V of 0 is equal to 0, you can remove the constraint that k is different from j. And this is exactly equal to the convolution of V with the empirical measure expressed at the point qj. So in other words, Newton's second law for each particle, you can view it as a differential system for the characteristic curves of the Vlasov equation localized at qj and pj of t, and therefore you propagate the solution by the solution of Vlasov exactly by Newton's second law, and the method of characteristics give you the result. So this is exactly the kind of property which we would like to see, and we would like to establish an analog of this in the quantum case, in the quantum dynamics. All right, so the problem, of course, is that in quantum mechanics, you don't have particle trajectories. So this notion of Dirac measures localized at phase space points, which you propagate, it's somewhat hard to conceive, right? It's not so easy to think what it could be. So instead of this, we're going to look at this problem from another perspective. And typically, the idea is to refer to this specific and characteristic property of empirical measure, functorial property, as Thierry said this morning, which indeed characterizes the empirical measure, and to use that in order to construct a quantum analog of the empirical measure. Okay, so let's see how it works. So so I'm going to denote by Gothic H, L2 of RD, complex valued, and Hn, the n-fold tensor product. So this is the n-particle Hilbert space. The first one is the single particle Hilbert space. So for k between 1 and n, I'm going to denote jk, the operator, the map, which to an operator on H associates the same operator acting on the kth variable in Hn. So in other words, I give you an operator, a single particle operator, A, and out of this, I'm going to look at an operator on the n-particle Hilbert space, which is acting only on the kth variable, and it's obvious how to do it. You just take the tensor product of A with copies of the identities everywhere except on the kth position. All right, so out of this, for each n larger than 1, you define an analog, if you want, of 1 over n, the sum over k of the Dirac measure at the phase space point zk, by looking at this quantity here. So you look at 1 over n, the sum over k of jk. So this is an operator from L of h to L of Hn, right? So this is a linear map from L of h to L of Hn. So that's my Mn initial. This is the, if you want, the analog of the empirical measure at time t equal to 0. And the next thing I do is I'm going to propagate it in time in the following way. So I choose my n-body quantum Hamiltonian as before, right? So script Hn is the sum over J of the kinetic energy of each particle. Sorry, there should be an xj, not xn. So it's the sum of the kinetic energy of the jth particle plus 1 over n, the sum of the interaction potential between the jth and the kth particles. So I assume that V is so that this script Hn has a self-valued, self-adjoint extension, right? So it's for, if you want, it's a self-adjoint operator. Okay, so this results from assumptions on V, which are well known, coming back to Cato, for instance. And since I know this is a self-adjoint operator, the quantum dynamics that it defines, e to the it script hn over h bar, is by Stone's theorem a unitary group. And what I'm going to do, I'm going to take mn initial, so the object which is here, I apply it to a single particle operator, A, that defines an element of L of Hn, so it's an operator on the n particle phase space. And I'm going to conjugate this operator by the n particle dynamics. So that's going to be the definition of Mn at time t, the quantum analog of the empirical measure at time t applied to A. Okay, good. So now let's see precisely the property that Thierry was mentioning this morning and how it applies to not only Mn at t equals 0, but Mn also at any subsequent value of time. So yeah, I'm going to look at trace class operators on Hn, which are symmetric in the sense that if I exchange particle labels, the operator is unchanged. So in other words, for sigma, a permutation of the particle labels, so for sigma in Sn, the symmetric group for the particle labels, and if I take psi n, a n particle wave function, I define u sigma of psi n to be psi n of x sigma minus 1 of 1, etc., x sigma minus 1 of n. So in other words, here we have a representation of the symmetry group in Hn, okay? And I'm going to call the n particle trace class operator symmetric if it commutes with this operator u sigma for all permutation of the labels Sn, okay? Good, so the characteristic property of Mn of t, which extends what Thierry was mentioning this morning for t equals 0, if I remember, is that if I take Tn of t, which is, I take some initial symmetric n particle trace class operator, I propagate it by conjugation with the quantum dynamics, and then I observe that if I take the trace of the first marginal of Tn at time t times any single particle operator, this is going to be equal to the trace of the n particle initial operator Tn initial times Mn of t acting on A, okay? So here I recall the definition of the first marginal of the partial trace. So here the partial trace means that I take the integral kernel of Tn of t. I take the diagonal, I restrict it to the diagonal for the n-1 last variable, says. I mean, I can do that for any other n-1 tuple of positions because the operator is symmetric. And I integrate over, say, Z2, Zn, and the result is an integral kernel on x and y, so it's an operator on H, right, on the single particle Hilbert space. Okay, so I can think of this Mn of t as being, if you want, the integral kernel of the linear map, which sends Tn initial to the first marginal of Tn at time t, right? So I can think of Mn of t in this way. So that's what this equality here says. We're going to use this identity to find an equation for Mn of t now, because we have Mn of t, and if I want to mimic what happens in the classical setting, I want to write an equation for Mn of t, and if possible, it would be very nice if this equation had something to do with the Hartree equation, okay? All right, so let's first write an equation for Mn of t, and here's the equation. So here I'm going to assume that V is in Fourier L1, even and real valued. So this Fourier L1 is, for technical simplicity, you can most likely take less restrictive assumptions, but let's take Fourier L1 at the moment for simplicity. Anyway, so the result is this. So IH bar del t of Mn of t is the sum of two terms, one which is add star of minus 1 over 2m h bar Laplacian acting on Mn of t, minus some interaction operator, script C of V, Mn of t, Mn of t. Now, of course, I have to explain what these two terms are. So the first one, I don't know if this, I don't know about this notation. This is like with the notion of co-adjoint representation, but there's no Lie algebra, no nothing here. So that's simply a notation. So what I denote add star of H acting on lambda of A, this is simply minus lambda applied to the commutator of H with A, where lambda is like Mn of t, any linear map from single particle operators to n particle operators. So you take any linear map from L of H to L of Hn. And you look at minus lambda of the commutator of H with A, and you define this to be add star of H of lambda acting on A. Good. So that's this piece here. The second piece is the interaction operator. And here's the expression for this interaction operator. So what you do, you take the Fourier transform V and you integrate with V hat of omega d omega. So remember that V hat is a L1 function now, and you integrate this difference here. So it's lambda 1 of E omega star. So E omega is the multiplication by the exponential of I omega dot x, right? So it's some kind of, it smells like some kind of Fourier transform if you want. So you have lambda 1 of E omega star times lambda 2 of E omega times A minus lambda 2 of A E omega times lambda 1 of E omega star. Now, this looks like a bracket. And indeed, if lambda 1 and lambda 2 would commute, this will be a bracket of, this will be lambda 2 of the commutator of E omega with A times lambda 1 of E omega star. But in general, lambda 1 and lambda 2 do not commute because they take their value in n particle operators. So we have this strange structure here, but this is reminiscent of a bracket as it appears in the Hartree equation. Okay, so that's the equation, and when you look at this equation here, it looks pretty bad because it looks like it doesn't have much to do with the Hartree equation. So it seems that the equation satisfied by Mn of t is not going to have anything to do with the mean field equation as in the classical situation. However, it's not a good idea to be, let's not be discouraged, say. And let's see, we have to remember in what sense a solution of Vlasov, a typical solution of Vlasov, has anything to do with an empirical measure. An empirical measure, it's a solution of Vlasov which is labeled, which is indexed by an n tuple of position and momenta. So if you take an individual solution of Vlasov, if you want, you can think of it as an empirical measure that would not depend on this n tuple of initial positions and momenta. So it's a good idea to look at, by analogy, it's a good idea to look at solution of this equation, which doesn't look so nice, for objects analogous to this Mn of t, but which are going to be constant, between quotes, in the initial positions of the n particles, right? So if you want to find something that's independent, that's a constant in your n particle system, the idea is to look for an object like Mn of t, so to look at a linear map from a single body operator to n body operators, that is going to be a scalar proportional to the identity on Gothic Hn, on the n particle Hilbert space. So the idea, of course, is to look at something like this. So you take a script R of t applied to A to be the trace of R of t times A times, so this is complex number, times the identity on Gothic Hn. So here, again, A is an operator on the single body Hilbert space, and R of t is going to be a time-dependent density operator on the single body Hilbert space, okay? Then you have the following observation that R is a solution of Hartree equation, which is written here for density operators. In other words, I h bar d by dt of R of t is the commutator of the mean field Hamiltonian with R of t. So I remind you that V R of t is given by this expression here. So you take the integral kernel of R of t, you reduce it to the diagonal, and you take the convolution with V. So that's the mean field potential. Okay, so your R of t is going to be a solution of the Hartree equation if and only if script R of t is a solution of the equation obtained in theorem A. So in other words, Hartree equation is a special case of this equation here, but for linear maps, for objects analogous to the quantum Klimantovich solution of this form, this special form. So if you want, you can think of them as chaotic Klimantovich solution in the sense that it does not depend, if you want, on the n particle initial data. Okay, so maybe let me say a few words about the proofs of these two theorems. First, maybe the fact that theorem A implies theorem B, which is perhaps easier. So you see that if script R of t A is given by this formula here, it's the trace of R of t times A times the identity on Gothic Hn. So if you look at the integrands of this complicated interaction term, so if you look specifically at this quantity here, where lambda 1 and lambda 2 are going to be equal to R of t. So what you see is an expression like this, right? So you see R of t e omega star, but R of t e omega star, if script R of t is given by this formula here, this is simply the multiplication by the Fourier transform of the density function corresponding to R of t. So in other words, this is the restriction of the integral kernel of R of t to the diagonal, right? And you take its Fourier transform in position. So that's this rho hat of t and omega multiplied by this quantity here. So, and here you have commutation. So, because this is simply multiplication by a number, right? So, I mean, this identity commutes to everybody, obviously, right? So here you have rho hat of t omega times v hat of omega, but that's the Fourier transform of a convolution. So here you see appearing v convoluted in x with rho, of which you take the Fourier transform in omega at time t. And here this quantity, if you compute it, this turns out to be the trace of the commutator of R of t with e omega. times A. And so here, because this is a scalar, you can bring it inside the trace. And you see immediately that this is the trace of R of t times the Fourier transform of VR of t at omega times E omega. And now what remains to be done is to integrate this in omega. So if you bring the integration in omega here, you see the VR as a function emerging as the inverse Fourier transform of its Fourier transform VR hat of t at omega. Okay, so that's essentially the proof of the fact that theorem A implies theorem B. So as for theorem A, the proof is a bit more complicated. So the idea is to start writing the first equation in the BBGKY hierarchy, which if you want is you take the first marginal of each side of the n-particle Schrödinger equation, or von Neumann equation, say. And you think of Mn of t at the adjoint of the map, which sends Rn at t equal to 0 to the first marginal. So it's exactly the functorial property that Thierry was mentioning this morning. And you have to represent the potential of x minus y, v of x minus y, as a superposition of tensor product of E omega of x and E of minus omega, or rather E omega of minus y. And once this is done, then at some point you will have to use this identity that if you look at Mn of t applied to A, commutator with Mn of t applied to B. So in general, these things commute, except for at t equals 0, you see that they commute, except that A and B are acting on the same particle. So at the end of the day, when you compute this, you'll see that it's 1 over n, Mn of t applied to the commutator of A and B. So if you use this formula here, plus the other ingredients, then you should arrive at the equation I was showing you. Okay, so I mean, for those who want to read the slides afterwards, I have more complete proofs written here, but I'm going to skip them in the interest of time. Yeah, so let me come to how you can apply this notion of quantum Klimantovich solution to the mean field limit, and specifically to the uniformity in h bar of the convergence rate. Okay, so so let me repeat what needs to be done. So you take V continuous and bounded on RD, even and real valued, and you're going to take possibly a family of initial data indexed by h bar, which has L2 norm equal to 1. So this is the initial data for Hartree, right? So you look at psi h bar of t and x to be a solution of the Hartree equation, to be the solution of the Hartree equation. H bar del t of psi h bar equals to minus 1 over 2m h bar squared, Laplacian of psi h bar, plus the convolution of V with the mod square of psi h bar times psi h bar. So this is the mean field potential, okay? And you assume that psi h bar at t equal to 0 is your initial data, your family of initial data with L2 norm equal to 1. And then you look at the n-fold tensor product of this initial data, like here. So this is the product of a j of psi h bar initial of the xj, which you propagate by the n-particle dynamics. So you apply to this the exponential minus it script hn over h bar, where I remind you that script hn is the sum of the kinetic energy of each particle plus 1 over n times the sum of the interaction potential for the particle at the position xj with the particle at position xk, and here j is less than k, say. Okay. All right, so this you call capital psi n of t and capital xn. Capital xn is just the n tuple of positions. So capital xn is x1, x2, etc., little xn. Okay, so we want to relate the reduced density matrix of this n particle wave function to the Hartree solution. And here is the result. So here I'm going to need more regularity on V. So specifically, I need that if I take V, if I differentiate it a number of times, which is equal to 3 plus d over 2, right? So this should be in Fourier L1. Okay, so that's so if you want you look at the Fourier transform V hat of psi, so it should be integrable with this weight. Okay, and all right, so I'm going to take so I call this V bold this integral here. And I look at capital gamma, which is going to be the max of 1 and the infinity norm of the Hessian of V. Okay. So both these things are assumed to be finite, of course. Okay. So now, if I look, the convergence rate is given by this formula here. So I'm going to look at the Wigner transform of psi n, of which I take the single particle reduced density operator. So if you want, I take the first marginal of the projection, the orthogonal projection on psi n at time t. And I want you to compare this with the Wigner function of psi h bar of the Hartree solution. So this is the Wigner function of the single particle reduced density matrix of the solution to the n-body Schrödinger minus the Wigner function of the Hartree solution. So I remind you of the formula for the Wigner transform, right? So if I give you a density R, which has integral kernel R of xy, so to compute the Wigner transform, I delocalize R across the diagonal by something of order h bar, right? So it's R of x plus 1/2 h bar y, x minus 1/2 h bar y. I take the Fourier transform in y, and this is going to be the Wigner function of R at x and psi. Okay, and here the norm in which I compare these two objects is going to be the dual norm of taking a function f and looking at the max of the L-infinity norm of f, of which I take at most n derivatives in x and psi. And I look at the uniform norm on these derivatives. Okay, so this dual norm here at time t is controlled by something that's independent of h bar. What is not so nice is that the constant here, the time dependence, is double exponential, but it's independent of h bar. And it's of the order 1/√square of n, right? So the good feature is that the case like 1/√square of n, like what you would expect normally. The slightly unpleasant feature is that you have a double exponential here. So, but in any case, it's uniform in h bar. Okay. Good. So let's see. Let me give you some ideas of how you prove such a result. So the idea is to use, of course, the equation for the Klimantovich solution. So you use this equation here, but you're going to apply Mn of t to a time-dependent single particle operator. And you choose this time-dependent operator in such a way as to eliminate as many terms as possible in the right-hand side of this equation here. And certainly you want to eliminate the kinetic energy part and also some part of the interaction integral. So you want to eliminate as many terms as possible here. So the way this is done is by taking A of t to be a solution of the linear Schrödinger equation, where the potential is going to be the mean field potential based on the Hartree solution. If you propagate A by this dynamics here, and if you look at script RT to be the chaotic Klimantovich solution, so in other words, this is given by this formula here. So you take your single particle operator B, you measure it with the Hartree wave function, and you multiply the results by the identity in Hn. Then you see that Mn at time t, there is no star, sorry about that. This is, there's no star here, sorry. So that's Mn of t minus script R of t applied to A of t is equal to Mn at t equals 0 minus R at t equals 0 applied to A of 0 minus I over h bar times the integral in time of this unpleasant interaction operator involving V, the difference between Mn and R at time s, and Mn at time s, okay? Okay, and you apply this to A of s ds. So essentially, what choosing this A has done is that you get rid of the unbounded parts of the dynamics here, which comes from the kinetic energy, and you make the difference between Mn of t and R of t appear in the interaction term. So hopefully at some point you hope that Mn of t in some sense is going to converge to R of t. And so it's a good idea certainly to make that difference appear. And well, you see this difference appearing in this interaction operator here. Okay. Good. So then you have to introduce a metric, which is a dual metric defined in this way. Again, no star here. I'm very sorry about this stupid star. So you take the soup of Mn at time t minus script R at time t acting on A of t, where A of t is the solution of this function here, which you evaluate on the initial n particle state, just given here. And here you assume that A at time tau, so you assume that along this trajectory at some time between 0 and capital T, you start from some Cauchy data, which turns out to be a Weil operator, where with symbol, which is less than 1 in this norm of which, yeah, in this norm with index n, right? So you measure the symbol so that it's less than 1. You propagate such an operator. You starting from a function like this, you take its Weil operator, pseudo differential operator with A as a symbol, and you propagate it by this dynamics here, and your dnt of t is going to be this soup here. Now, the thing is that if you want to control this dn of t, then you will see something rather nice appearing. So you see, the difficulty is here is that you have the 1 over h bar, which is going to be annoying for the uniformity which you want to achieve. But this 1 over h bar, you have to balance it with the commutator structure that appears in this interaction operator here. So to cut a long story short, the thing that you observe is that if you look at 1 over h bar, the norm in this integral, what will appear is 1 over h bar times the norm of the commutator of e omega with a of t. And this e omega, that's the multiplication by by the exponential of I omega dot x. If you take the commutator with a while operator, then it's easy to control the norm, because the commutator of, say, exponentials of while operator is simply computed in terms of the symbol. So here, the thing is that this 1 over h bar, the norm of e omega with a of t, is controlled by a quantity like this, which is naturally propagated and which is of order h bar at the time on this trajectory where a of t is a while operator, and then it's propagated by a unitary dynamics. So essentially, here you will have h bar that will appear and kill the 1 over h bar, which is here, at the expense of an extra omega here. Okay, so so you use this estimate here to kill the 1 over h bar, and then at the end of the day, if you return to this integral formula here, you see that the difference at time t between the Wigner function of the reduced density operator, the n particle wave function, and the Hartree solution in this dual norm is controlled by this dn at time t. And this guy, if you look at it at capital T equal to 0, you prove that it's controlled by a constant over square root of n by a variant of the Calderon-Vaillancourt theorem, where you know exactly how many derivatives of the symbol you involve, right? So this is a rather technical part of the proof, because it uses some semi-classical estimates, but these are really not so technical estimates. The most technical part is probably this Calderon-Vaillancourt piece, but it can be used as a black box. Okay, and part 1 and 2 are mostly algebraic, so that there is no hard analysis part here. Okay, so that tells us that gives us the mean field limit uniformly in H bar. Let me finish with a few observations for how this framework, how this setting compares with earlier results on the mean field limit. So perhaps the first thing I want to say, discuss is the case of Coulomb potential, because here we have dealt with very regular potentials, but in quantum mechanics, you might want to treat the case of Coulomb potentials, for instance, in atomic physics. Having regular potential is not completely satisfying for that purpose. So the mean field limit with Coulomb potential has been treated by many authors, at least when you don't take h bar going to 0, if you just look at the mean field limit and you don't take a classical limit with it. So you have perhaps the first result, which is due to Erdős and Yao in the early 2000s, I think it's 2002, Advances in Theoretical Physics, beautiful paper, based on BBGKY hierarchy. Then after that, you have a result by Rodnjansky and Schlein. And at about the same time, there's a very nice paper by Peter Pickel, which found a way, rather simple proof of this limit. And it turns out that the Pickel proof can be expressed or can be couched in terms of this quantum empirical measure as well. Let me explain that. This is an observation with my student, Emmanuel Ben-Porat. So, okay, again, so I start from my n particle Hamiltonian, quantum Hamiltonian, and I assume that V satisfies the Cato assumptions from this Cato 1951 paper, right? But I'm going to need more than this. I'm going to assume that as an operator, V squared is controlled by a constant times identity minus Laplacian, okay? So in space dimension 3, Coulomb potential is obviously included because of Hardy inequality, which you can write as 1 over the norm of x squared, which is less than or equal to 4 times minus Laplacian, right? So you don't even need the I here. Good, so you start from a solution of a Hartree equation, and here I'm going to assume that the initial data is in H1, and okay, so here is the observation. So first, you consider Mn of t to be the quantum Klimantovich solution for your n-particle dynamics, quantum dynamics. And you look at the chaotic Klimantovich solution, if you want, the morphism, which is built on the Hartree solution. So you take your favorite single particle operator A, you compute it in the state which is given by the Hartree solution at time t, right? You multiply, so here, sorry, this should be a Gothic Hn, right? There's an n missing here. So A is a single particle operator, but script R is an n particle operator. Okay, and then you let the projection, you let P of t to be the projection on the line spanned by the Hartree solution. And the first observation is that if you look at Mn of t applied to identity minus this projection, it satisfies an equation. So you have IH bar del t of Mn of t applied to identity minus P of t. This is the interaction operator script C, this horrible interaction operator, acting on Mn of t minus script R of t. Script R of t is here, Mn of t. And this interaction operator is applied to identity minus P of t. Okay, now if you look at the right-hand side of this equality here, which you divide by IH bar, turns out that as an operator, so this right-hand side is going to be a self-adjoint operator. And the self-adjoint operator turns out to be comparable to this Mn of t applied to identity minus P of t, but there's an equality in the sense of operators, right? So this plus or minus I, curly C, this interaction term is controlled by some function of time times the thing which you have on the left-hand side, modulo an error, which is of the order 1 over n. Good. 1 over n times identity. Okay, and as a result, then if you take Rn of t to be the initial factorized, you take the n-fold tensor product of the Hartree initial data, which you propagate by the quantum dynamics and particle dynamics, then its first marginal minus P of t in operator norm is going to be controlled by constant over square root of n times the exponential of 1 over h bar times this function of time. So this is pretty much the same results as obtained by Picker and Knowles. Yeah, I mean, the Pickle's original idea was to look at 1 minus the first marginal of the n-particle density operator evaluated on the Hartree solution. And to prove that this quantity script En of t satisfies a Grunwald type inequality here. So here, the idea, well, it's not very much of an idea, it's an observation, is that En of t turns out to be the quantum Klimantovich solution observed or evaluated on the n particle wave function. Okay, and so this is again the factorial property mentioned by Thierry in the morning, and you use this equation satisfied by this object and this inequality here to recover the same Grunwald inequality that was obtained by Pickle and Knowles. But if you want, there's an inequality at the level of operators without taking the applying it to this n-fold tensor product of initial data. So if you want, the Pickle method can be formulated with this quantum Klimantovich case setting. Yeah, I mean, Rodniansky-Schlein was very much in the same league. It's the same type of results as Pickle, so it's comparable to this one as well, except that it uses second quantization techniques. There's another approach to this problem, but which seemed limited to Toeplit's initial single body density, which we obtained with Clément and Thierry already 5 years ago, and which involved a quantum analog of the notion of Wasserstein distance of x1 and 2 for quantum densities. So that's another way of obtaining a uniformity in H bar, if you want, for this mean field limit. Yeah, I should mention there's the earliest results on uniformity in H bar, the mean field limit, are due to Graffi, Martinez, and Puviranti, and to Pezzotti and Puviranti already some time ago, by other techniques, as mentioned here. And also, I should mention a beautiful result by Sylvia Serfati and Mitya Dwerings, which appeared in Duke last year, which essentially they prove the classical mean field limit, but in a monokinetic regime, and they have a beautiful inequality for the Coulomb potential, which is absolutely essential here. And with Thierry, we looked at the quantum analog of this limit, where you have both the mean field limits and the classical limits taken independently. So if you want to have the 1 over n plus h bar converging to 0, I mean, on this problem, you might use a quantum Klimantovich solution, but it turns out that it's not necessary. You have a simpler proof, which is going to appear in this paper here. Well, of course, it's the same nature, but somehow you don't see the quantum Klimantovich stuff so much in this paper. I mean, you can pretty much avoid it. Okay, so to conclude, yeah, well, I mean, this property A is an extension of the Klimantovich theorem, which is the kinetic theory excuse for this talk, and we use it to obtain a 1 over square root of n convergence rate for the quantum mean field limit uniformly in H bar. So there are several extensions, perhaps, yeah, I mean, I've been recently working with Samir Salem on applying this formalism of quantum Klimantovich solution to fluctuation theory, as in the paper by Brauneheb and in the classical case. There's an earlier result, I think, by Benarous and Schlein and someone else, whose name I've forgotten, which appeared maybe 10 years ago on this problem, again, using second quantization techniques. I suspect that, well, I'm pretty sure that using quantum Klimantovich solutions could give the same results or the same type of results without the second quantization formalism. And finally, the discussion in this talk applies to bosons, and it will be quite interesting to see if it can apply to fermions. There's of course, an important series of works by several authors: Benedicte, Jaksic, Laurent Laflèche, Radmacher, Chiara, Safirio, Benjamin Schlein on the subject. I suppose that it's already well known for about little less than in the past 10 years. So it would be good to see, since one has uniformity in H bar here, whether this can say anything about the fermion case. Would be nice. Okay, thank you very much.
Thank you, Francois. Thank you. So, questions, comments in the audience? Please unmute yourself. Chiara, yeah, please go ahead.
Maybe there was one point in this last part when you were comparing with the previous results that I was a bit confused, and now I'm even more when you say that this all applies to bosons, because isn't the paper by Antti and Peter for fermions? So
which paper?
By Antti Knowles and Peter Pickel, the 2009. So it looks like now you have a bosonic version of their methods.
Perhaps.
So
if it applies to fermions, would be a good news. So I don't remember, because I've not looked at this paper in quite a while. So I may. No, I mean, yeah, perhaps. Let me say one thing. So in the original Pickel paper, the thing that appeared in Letters in Mathematical Physics, right? He doesn't quite treat the Coulomb case. So that I'm quite sure, because he has to assume that V is in a Lebesgue space, which of course the Coulomb potential is not. So where I may have made a confusion is that I think I took from the paper with Knowles this inequality. I think I took their paper. It appears in this inequality. It appears in this operator inequality. And once you have this inequality, I mean the rest is standard. So it could be that I have attributed to Knowles and Pickel something which was in Pickel plus this condition. Maybe I'm wrong at this point. So I'm going to check.
Okay.
Yeah, I'm sorry about that.
No problem. It's so then it's not just a rewriting. It's something. It's not a rewriting with a new method, but seems like a different result. Still for H bar fixed.
Yeah. But it's. I think once you have the look, I mean, if you had the Pickel result with the Pickel result extending it to Coulomb, I don't think it's a very big extension, right? I don't know. I hope otherwise. Yeah. No, I think it's the same type of result. Thank you. Thank you for pointing this.
No, thanks for the nice talk.
Thanks.
Any other questions, comments? It seems it's not the case. So thanks. Thanks again, Francois. Okay, so we have a short